Well, welcome again to our journey into number theory, in particular analytic number theory. And we're going to move on now and have a look at L functions. We've talked a little bit about characters and Dirichlet characters. And we're going to now use the Dirichlet characters to define these very important things called L functions and introduce the generalized Euler product. So Dirichlet generalized the zeta function and found an analog to the Euler product. So this goes back to Dirichlet. The Euler product, you'll recall, was this amazing identity here that the product over the primes of 1 minus p to the s inverse is just equal to the zeta function. And this, of course, makes sense and converges if s is bigger than 1. Now, from now on, unless otherwise stated, and I will occasionally state it, we're going to think of s now to be a complex variable. And you can check that the series converges if the real part of s, which we generally call sigma, if the real part of s is bigger than 1. We'll come back to that a little bit later as well. Using this, Dirichlet was able to generalize the proof that I did in an earlier chapter of the divergence of sigma 1 over p prime from the set of all primes to sets of primes of certain shape, in particular in those in arithmetic progressions. And that result, of course, is known as Dirichlet's theorem, and that's what this chapter is all about. So given a Dirichlet character modulo n, remember what that means. We start off with an integer n, we map it into un, and then we use the character, the ordinary group character, to map it from there into the complex numbers. We define an L function, L of s and chi, by this sum. And if you look at it, all we're doing is we're just replacing the 1 up here in the Riemann zeta function by chi of n, this Dirichlet character. Now, happily, if we take the modulus of this sum, then this is less or equal to sigma 1 over n to the sigma. So this is little sigma. Sigma is the real part of the complex number s. And, of course, this series converges. This series converges for a real part of s bigger than 1, if sigma is bigger than 1. And so it converges, in fact, uniformly on any compact subset of the region real part of s bigger than 1. We're now going to consider, as we did before when we were looking at the Euler product, we now look at a corresponding product. We're going to look at 1, before we looked at 1 plus 1 over 2 to the s, 1 over 2 to the 2s, and so on. And now we're going to replace that with the characters. So we're going to look at the sum 1 plus chi of 2 on 2 to the s, chi of 2 squared on 2 to the 2s, and so on, and multiplied by this, and so on, where these, of course, are all prime numbers. So the next one after the 7 would be 11. Now, of course, as before, we can, these are just geometric series, so I can sum each of these using the fact that chi is multiplicative, and we end up with this product as we saw before. It's the product over the primes of 1 over 1 minus chi p to the power s. And you can see that that is analogous to what we had up here for the zeta function. We're just replacing the 1 here now with a character. On the other hand, as we did before, if we take a deep breath and expand it all out, then we get 1 plus chi 2 on 2 to the s from there. We'll get a chi 3 on 3 to the s from there. We'll get a chi of 4 on 4 to the s from there, chi of 5 on 5 to the s. The 6 we'll get from multiplying these two terms here, and so on. And again, by unique factorization and by the fact that chi is completely multiplicative, we obtain this, and of course that is just our L function. So we can now state that for the real part of s bigger than 1, we now have this, we can write this lovely new L function as a generalized Euler product, or an analog to the Euler product of 1 minus chi p on p to the s, or inverse. Now, we're going to get to the, I wanted to do some examples firstly of just looking at what these L functions look like. So just to have a look quickly at a couple of examples. So If we're looking modulo 8, then I can take a character, which I've called chi2 here. So the, the elements of U8 are 1, 3, 5, 7. And I'm going to take this character chi2 that we looked at before. This is an ordinary character, not a Dirichlet character, an ordinary character at the moment. And this particular character, of course, sends 1 to 1, 3 to -1. 3 squared is 1, and 5 squared is 1, and 3 by 5 is, what's that, 15, that's 7, so that by that gives me that one. So there's the character. This is the ordinary character table. Now I'm going to think of this as a Dirichlet character, which simply means I can move this modulo 8 further on, and I can write down my L series for this. So L of S and chi2, well, it's 1 over 1 to the S. Now I get -1 over 3 to the S. Remember, we're now looking at the Dirichlet character, and that's going to send 2 to 0, because 2 is not relatively prime to 8, and takes that value for 3. It maps 4 to 0. 5, its character value is 1, so it's 1 on 5 to the S, -1 on 7 to the S. Now, this is now a Dirichlet character, and so 9 is congruent to 1 mod 8, and so the whole thing cycles back. It's got period 4, and so we just continue on 1 over 9 to the S, then we get -1 on 11 to the S, and so on. +1 on 13 to the S, ... So that's what these things look like. This is how we calculate with them. Just as another example, if we look mod 5, this is an ordinary character. So in U5 we have 1, 3, 4, 2, 3 is the generator. And one of the characters we did in an earlier example was chi3, which maps 1 to 1. We send 3 to the 4th root of unity I, and 3 squared is 4, so I squared is -1, and then 3 by 4 gives me 2, and you multiply those, you get that. So this is the, I'm abusing notation somewhat, this is the ordinary group character, and this here is the Dirichlet character. And so we'll do the same thing again. We form our L function by taking 1 over 1 to the S, then now for 2 we have -I on 2 to the S, -I on 2 to the S, and then +I on 3 to the S, -1 on 4 to the S. Now 6 is congruent to 1 modulo 5, so this again is just going to cycle back. So we have 6. There's no 5, of course, because 5 is 0 mod 5, so that its character value, its Dirichlet character value is 0. So we get 1 on 6 to the S, and then it just cycles through, -1 on 7 to the S, +1 on 8 to the S, -1 on 9 to the S, and then the next one would be 1 over 11 to the S. So just so that you get a bit of a feel for what these things look like. So they're just infinite series with powers of S in the denominator, and the powers here, the numbers relatively prime to the modulus, and then we get the character values on the top, which may be complex numbers, they may be real. Now, we rather than launch straight into a proof of Dirichlet's theorem, which is quite technical and takes a bit of a deal of understanding, I'm going to spend a little bit of time to see the key ideas that are going to appear in the proof of the result, and I want to see them displayed in some examples. So in particular, I'm going to return to the problem of showing that there are infinitely many primes congruent to 1 mod 4 and infinitely many primes congruent to -1 mod 4. This is a fairly longish example, but it's a very important one and worth spending some time on, because we're going to use similar ideas when we come to the main proof of Dirichlet's theorem. So this is a little warm-up to Dirichlet's theorem. So we're going to be looking at things modulo 4. There are 2 Dirichlet characters mod 4, and the table for these are now, again, I'm abusing the notation a bit. This here is the ordinary character table for U4, and then we're going to extend it to a Dirichlet character in a moment. So chi1 is our principal character, maps everything to 1. Chi2 sends 1 to 1, and then 3 goes to the other square root of 1, which is minus 1. Now we can now look at the Dirichlet characters, which take the integers and map them into U4 and then up into the complex numbers by using the character values. So we can see that for chi1 everything gets mapped to 1, but any integer which is not relatively prime to 4 gets mapped to 0, i.e. if n is even, then chi1 of n is 0, and if n is odd, well, the values are all 1 as it cycles through. Chi2 is a little bit more interesting because again it's 0 if n is even. Now if n is 1 mod 4, then we take the value 1, and if n is 3 mod 4, i.e. minus 1 mod 4, we take the value minus 1 for the Dirichlet character. We can now write down the L function for example, chi of 2. We'll come back to chi of 1 in a moment, but the Dirichlet character for chi of 2 is for s bigger than 1. Here, there's no complex values in the character table, so everything, we may as well think of everything as real and take s bigger than 1. So L of s and chi2 is this sum. That's how we defined it. And now it's just 1 over 1 to the s minus 1 over 3 to the s plus 1 over 5 to the s minus 1 over 7 to the s. And the corresponding Euler product is this thing here. It's 1 minus chi2 of p on p to the s, p an odd prime. For the principal character, well, it's very similar. Again, it's defined to be that, and so we just write the series out. We're only going to get odd numbers down here, and all the character values are 1, and its its Euler product looks like this. The chi value is all 1 here. Now, what we want to do with this, I want to play with the Euler products, and at the moment they've got a minus 1 up here, which I'd like to get rid of, and I'm more happier with sums and products, and so I want something that turns a product into a sum, and so we're obviously thinking of logarithms. So for s real, s bigger than 1, I'm going to take the log of L of s and chi1. You recall we did a similar sort of thing when we were looking at proving the divergence of sigma 1 over p. So when we take the log, the minus comes out the front. I get a sum over the odd primes of log of 1 minus p to the s. And I simply use the Taylor series expansion of minus log of 1 minus x, and replace x with p to the s, and it looks like this. So I've just expanded the minus log 1 minus 1 over p to the s as a Taylor series and written it in this way. Now what we do is then we're going to peel off, again this is by analogy with what we did earlier when we're looking at sigma 1 over p. I peel off the first term, plus I get some remainder. I get the tail of this infinite series. Now I want to look at the tail and see if we can get some control over the tail of the series. So R1 of s is just the sum over the primes of all these terms here, and that's just what I've written down here. And I just start bounding away things. So this is less than, I can replace the 3, 4, 5 with just 2's all the way along. That turns this into a geometric series, which I can sum, and I get this. Simplify gives me this, multiplying top and bottom by 2p to the s. Sorry, 2p to the 2s, and I can factor out. And I'll toss away the s. S is bigger than 1, so this sum is less than this sum. Now these are all sums over the odd primes. So the sum over the odd primes is certainly less than the sum of all the integers from 2 upwards. And if we this one I can do as a telescoping series. I can take the half out the front, partial fraction, telescoping series, this thing collapses down to a half, which I'll leave you to check the technical details of. So that tells me then that R of 1 of S is bounded as S goes to 1 from above. So for any S, this one is bounded. So we'll just keep that in mind. Now let me put all that together and summarize that. So summarizing this, we now have that the log of L of S and chi1 is sigma over sum over the primes 1 over p to the s plus R1 of S. So this remainder term, but the remainder term is bounded as we go to 1. Now similarly, we can do a similar thing for the L of S and chi2. So from the Euler product, from that we can proceed exactly as before. I won't go through all the details again, but except this time we now end up with a chi2 of p on the top and not a 1. But all the rest of the calculations are exactly the same. Now again, we'd like to know how big this is. Well, happily the modulus of this is, because this number here is of modulus, chi2 of p is of modulus 1, so this is just less than R1 of S, and that tells us that R2 of S is bounded then as S goes to 1 from above. And so now we have these two expressions. Now, just observe that if you take 1 plus chi2, remember chi2 is 1 if p is a 1 mod 4 prime, and that means you get, this is 1 plus 1 is 2 if p is a 1 mod 4 prime, and this is minus 1 if p is minus 1 mod 4, so that gives you 0. Similarly, if I take 1 minus this, then we get the other way around. We get 2 if it's a minus 1 mod 4 prime, and it's 0 if it's a 1 mod 4 prime. Now that's very nice, because that means if I now take the sum of these two logarithms, if I take the log of L of S and chi1 plus the log of L and S and chi2, then because of what we see up here, when we're taking the sum, I'm going to get 0 if I've got a minus 1 mod 4 prime, but I'm going to get 2 if it's a 1 mod 4 prime. And so I'm simply going to get twice 1 over p to the s, p congruent to 1 mod 4, because in that case chi2 of p is 1, and I can combine that with the 1 over p above, and I get 2 of those, plus I get another remainder term, which is just going to be R1 plus R2, as we observe here. So R3 is just R1 plus R2, and these are bounded. And similarly, if I take the difference of the two, then by what we have here, this is going to give me twice sigma 1 over p to the s for the minus 1 mod 4 primes, plus another remainder, another tail, and that's just the difference of these two, and both of these are bounded as s goes to 1 from above. So let me just label these 1 and 2. Now let us just enjoy the first identity here, because what we're going to be able to say now, we're going to let s go to 1 from above. And we're going to show that, well, we know that this thing here is bounded. We're going to show that this thing here is also bounded. We're going to show that this one diverges off to infinity as s goes to 1 from above. And that's going to tell me that this sum must diverge. And that's going to tell me there are infinitely many primes 1 mod 4. And the same argument's going to work on this line here. That's bounded. We're going to prove this is bounded. We're going to show that should be chi1 there. We're going to show that this thing here is not bounded, that this goes off to infinity as s goes to 1. And that means this sum goes off to infinity as s goes to 1. And that means there are infinitely many primes congruent to minus 1 mod 4. So all we need to do at the moment then is to show that the next key step is to show that these ones here, we need to show in particular that L of S and chi2 is bounded away from 0, because we're taking a logarithm, so we don't want this to go to 0 as s goes to 1, and we don't want this to diverge either. So we need to show that L of S and chi2 is bounded away from 0 as S goes to 1, and we need to show that this one diverges, that this goes to infinity, that L of S and chi1 goes to infinity, and therefore so that does its log as S goes to 1. So that's the next part of the story. And to do that, I'm going to use some fairly ad hoc methods here with these sorts of examples. We'll see better ways of doing this later. So, so L of S and chi2, I've just written out what it is again. So it's 1 minus 1 over 3 to the S plus 1 over 5 to the S minus 1 over 7 to the S, and so on. Notice I've bracketed these judiciously in this way, and I'm just going to say, well, each one of these brackets is positive. 1 on 5 to the S minus 1 over 7 to the S is positive. So I can toss away all of that and just get left with this using an inequality. And again, I can toss away the S and write this as bigger than 1 minus 1 over 3, which is 2/3. Now that's very important because that means it's bounded away from, well, it's bounded away from 0. It's, as S goes to 1, this thing is bigger than 2/3, and so it's certainly bigger than 0. On the other hand, I've got to show that it doesn't diverge, and so again I write the terms down, but I've just re-bracketed slightly, so I've taken a minus out of that and bracketed these two together, and then I've taken the 7 and the 9 and done those together. And now each one of these brackets is positive. Each one of the terms in the brackets is positive, so this is 1 minus something positive minus something positive, and so on, and so that's going to be less than 1. So that tells me L of S and chi2 is bounded by this, and it's bounded away from 0 by this, and that's for all S bigger equal to 1, and that means log of L of S and chi2 is finite. So the logarithm is finite as S goes to 1 from above. Now, you might at this stage be screaming a little bit and saying, well, hang on a minute, you've rearranged the infinite series. And one has to be very careful about arguing that way, and so I just, for the sake of argument, let me just point out here that L of S and chi2, if you actually write the sum out, it looks like this. It's just the odd numbers in the denominator, and then it's alternating. And if you look at this alternating series, you can see that it's absolutely convergent, because the corresponding non-alternating series, which is 1 over 2 to the n plus 1 s, provided s is bigger than 1, then this is, provided s is bigger than 1, this is going to be absolutely convergent. And so therefore for s bigger than 1, I can rearrange the terms of this infinite series without penalty. Now, on the other hand, L of S and chi1, well, again, if you just write down what that was just the sum of the s powers of the odd numbers, and clearly that does go to infinity. As s goes to 1, this is not alternating anymore, this is going to go to sigma 1 over 2 to the 2n plus 1, and that one will diverge as s goes to 1 from above, and that means its logarithm diverges as s goes to 1 from above. Finally, putting that all together in line with what we've just been saying, as s goes to 1, from equations 1 and 2, as I mentioned, we have that both of these infinite series diverge, and that means there are infinitely many primes of each type. So that was designed as a warm-up to the Dirichlet proof, and gives you an idea of roughly the steps we're going to be going through in order to give a full proof, which we'll have a look in start in the next section.